Welcome to our third installment of the homework discussion for the Titelbaum book. This is homework discussion of Chapter 3. Chapter 3 has 4 problems, which are going to be on the take-home final. So we'll have to make sure we skip those. Those are numbers 3, 4, 8, and 12. All right, the first problem is one of those problems. You probably had some of this when you were in school too, where the problem isn't that difficult itself, but it's made complex by making you do the same thing over and over and over again. And this time we have to do it 30 different times. So that's the frustrating part about it. So you're asked to calculate what's the probability that when there are 30 people in a room, 2 of them share a birthday. And I think the easiest way to solve this is to use the negation rule. So what we're going to do is try to figure out what the probability is that there are no shared birthdays among a certain number of people. And the way you do that is you imagine the people coming into the room in sequence. So the first person comes into the room, and obviously that person has no chance of sharing a birthday with somebody in the room. So we use 365 over 365 for the probability of not sharing a birthday for the first person. For the second, there's 364 days left. So the probability for 2 people sharing a birthday is 364 over 365. It's basically 1 times that number, which of course is just that number. And then you just keep going down, removing 1 of the 365 days for each succeeding person to come into the room until you get to the number n that you're looking for. And if you like mathy formulas, here's the formula that you would use to solve that. And when we solve where n equals 30, we get the probability is 0.293 of no shared birthdays with 30 people in the room. So the probability that they share a birthday is 1 minus that, or 0.707. Okay, here's 3.2 is merely meant to illustrate to us that sometimes even ordinary human beings will end up assigning irrational numbers as credences, given the commitments that they have. So you're supposed to take these 3 conditions, 1, 2, and 3, and figure out what the credence distribution will look like. So here's the answer. Probability of y and not y are the same by 2, so they both have to be 0.5. Y is logically equivalent to x and y, or not x and y. So we can derive that the probability of x and y or not x and y is also 0.5. Now this disjunction is exclusive, so you can calculate it just by adding the first probability, the probability for the first conjunction, plus the probability of the second. And then according to the third condition, those 2 conjunctions have the same credence, so they both have to be 0.5. Given that result, we can then rewrite this first condition using the ratio formula on the left side of the equation and using the general disjunction rule on the right side. So the probability of y and x divided by the probability of x is probability of x plus the probability of y minus the probability of their conjunction. Now we know both of those 2 numbers. They are 0.5 and 0.25 respectively. So when we get done with the simple arithmetic, we end up with the probability of x plus 0.25 on the right side of the equation. And we also know this probability in the numerator, it is 0.25. So we end up with a formula where the probability of x equals 0.25 over the probability of x minus 0.25. And I'll show you the solutions that the math equation editor calculator that's on the web gives for this. There turns out there's two solutions to this. That's not surprising. But one of them is a negative number, so no probability can be a negative number. That leaves us with this one. Okay, so here are the details. I'll let you go through to convince yourself that each of these steps is correct. You solve for x. You end up, before converting to a decimal, with this fraction, which is clearly an irrational number. And there are then two solutions to this, but one of them is negative, so we pick the positive one. So 3.5, we'll pick back up at 3.5, and it's about proving Bayes' theorem, which is an incredibly easy proof. So start with, here's where we're headed. There's the simplest version of Bayes' theorem. Probability of H given E is the probability of E given H times the probability of H over the probability of E. So start out with the ratio formula. Probability of H given E is the probability of H in E divided by the probability of E. The probability of H in E is the probability of H times the probability of E given H. And multiplication commutes, so flip them around and then substitute that in for the numerator on the ratio formula, and you get Bayes' theorem. Very easy proof. Now, one thing that we will do later on and quite often in solving problems is do an expansion on E. So the expansion, let me pull up my little annotating tool. So we're thinking of our logical space in terms of a big block of some sort. I think of it as a block of cheese, but you can think of it as whatever you want. Chocolate? Anybody for chocolate? In any case, this block is divided somehow in terms of in parts to E and not E. And when we're using Bayes' theorem, these prior probabilities are always problematic. You want to know, where do they come from? How do we get the numbers? And it's pretty clear there's no alternative to getting the probability of H in the numerator. So let's just assume we're going to have to get the probability of H from somewhere. But we also have this unconditional probability of E in the denominator. And we can get rid of that unconditional prior probability by doing an expansion on E. You get an expansion of E when you cut the partition in some other terms than E to start with. So for example, doesn't have to be a straight line, doesn't matter what it is. Suppose you partition the space into an H and a not H part. Well, you know that E is logically equivalent to E and H or E and not H. And you know that that disjunction is exclusive. So you can just add the two. And that lets you do an expansion on E, where what you're doing is adding the probability of E and H together with the probability of E and not H. And you also know that that probability is the same as the probability switched around in the other order. So let's put the H first. And then if we take the probability of H and E, we get this again, probability of H times the probability of E given H. And if we turn this side around and do the same thing, we get the probability of not H times the probability of E given not H. So now we need these two conditional probabilities of E given H and E given not H. But the only unconditional probabilities we have left are derived from the probability of H itself, because probability of not H is just going to be 1 minus the probability of H. I call this the logical expansion on E relative to this partition. And you can see that if you decided to carve up the space in terms of a more fine-grained set of partitions, it doesn't matter how you do it as long as it's a partition. A partition exhausts, it gives you compartments that exhaust the entire space and don't overlap with each other. And then all you do is you say, well, E will be equivalent to E plus the first thing, plus E and the second, plus E and the third, plus E and the fourth, plus E and the fifth, on down until you get to the last one. And then you're done. That's the probability of E. Summing all of those probabilities for E on each partition. That often makes problems easier to solve. So we typically won't use this simplest version, but once you get the simple version, you can prove the more complex ones just by the logical equivalence claim, where you note that E is equivalent to any of the expansions that you're after. Okay, exactly what unconditional credences must we assume to be positive in order for the proof to work? Well, the probability of E can't be 0. Otherwise, the ratio formula can't be applied to H given E. Where does your proof rely on the probability axioms? Well, we relied on logical equivalence, so whatever we use to prove logical equivalence will be needed for this. Okay, 3.6 and 3.7 are not on the exam, so let's look at 3.6. All right, here's a credence distribution across P, Q, and R. That's a truth table for P, Q, and R with the credences attached to each one of the state descriptions. So this is very, very simple work. Just apply, we're calculating now conditional probabilities. And so in each case, you apply the ratio formula, generate a fraction, because the ratio formula tells you that this credence is the credence for P and Q divided by the credence for Q. So then you go and you find what's the credence for P and Q. Well, that's lines 1 and 2 on our truth table. So that's 0.3. And then what's the credence for Q? That's 1, 2, 5, and 6. That sums to 0.6. 0.3 over 0.6 is 0.5. So relative to this distribution, is Q positively relevant, negatively relevant, or probabilistically independent? Well, for that, we need to know what the probability of what the credence for P is, and that's the sum of 1 through 4, and that's 0.6. So this credence is lower than that one, so it's negatively relevant. All right, a couple more examples. What's the credence of P given R? You do the same thing that I did before. Look for lines, look for the P and R lines and divide that by the R lines, and you get 0.5. What's the credence for P given Q and R? Do the same thing. Look for the credence for P and Q and R, that's 0.1. Then look for the credence for the Q and R lines, that's 0.2, so you get 0.5. At step 3, conditional on R, is Q positively relevant, negatively relevant, or independent? The answer is it's independent given R because the two probabilities come out the same. Does R screen off P from Q? So screening off requires 3 claims. The first one is what we had in the answer to problem E. These two probabilities have to be the same. They have to stay the same when you replace R with not R, and they do that. And then we have to have the relevance of P for Q, which we do have in our answer to B. So yes, screening off is present. All right, independence. Probabilistic independence is defined in 3.14 this way. the credence for P given Q is the same as the credence for P. That's what it is for P to be independent of Q. Now, it turns out that there are a number of different ways, logically equivalent ways to say that, and the numbered claims in question are these first four lines. So that's 3.15, this one's 3.16, then 3.17, and 3.18. And so we're being asked to prove each of these, given that we already have 3.14 and the probability axioms in the ratio formula. So the ratio formula says the credence of P and Q is the credence of P given Q is the credence of P and Q divided by the credence of Q, and that will equal the credence of P. So let's start with the last one. None of these are very complicated, but let's prove the last one first. We note that P and Q is equivalent to Q and P, so the credences are the same. By the general conjunction rule and 3.14, we need only multiply for the former conjunction. We need only multiply for the former conjunction. So the same is true with the latter. I think this was supposed to say, let's hold off and come back to 3.18 because there's something confusing to me about what I was thinking. I don't think this is supposed to be the word conjunction. I think it's supposed to be something else. So look at line Well, let me just run through what I have here. Next comes 3.16, which is this one. And we use 3.18 to show that the two numerators are simple multiplication problems, with the second factor the same as the denominator. By algebra, the second factor and denominator cancel out, leaving us with the claims. Leaving us with the credence for P being the same as the credence for P. Let me stop for a moment and go back. There's a mistake here that I need to fix, and then I'll come back and we'll try this one again. Okay, I cleaned up the explanation of 3.18, which will help us see easier how the proof is supposed to go. So let's start with the last claim, that the credence of P and Q is just the product of the individual credences. So we note that P and Q is logically equivalent to Q and P, so the credences are the same. By the general conjunction rule, this second claim, Q and P, is gotten simply by multiplying the probability of Q times the probability of P given Q. And this latter probability is, by 3.14, just the probability of P. So 3.18 is proved. Let's turn to 3.16 next. And here we use the fact in 3.18 to show that after applying the ratio formula to both sides here, the two numerators are simple multiplication problems of the unconditional probabilities of the two conjuncts, with one of those two being the same as the denominator. By algebra, the second factor and denominator cancel out on both sides, leaving us with the claim that the credence for P is the same as the credence for P, so 3.16 has to be true. Now, if that was a bit murky, just look at it like this. Apply the ratio formula to this, and you get P and Q, the probability of P and Q, over, I'm leaving off the probability operator sign just to make it quicker. You get the probability of P and Q over the probability of Q, and given what we showed in 3.18, you can just multiply across the top. So you've got the probability of P times the probability of Q divided by the probability of Q, and those two cancel out. And on the other side, you'd have the probability of P times the probability of not Q over the probability of not Q, and that cancels out. So this is true if and only if the probability of P is the same thing as the probability of P, which of course it is. Okay, so we have now 3.18 and 3.16, and this fact establishes 3.17, the one with 3 claims, all of which are identical. The first equality between the credence of Q given P and the credence of Q is simply 3.14. All you need to do is switch the Q and P positions around. So this is an instance of 3.14. And then the third equality claim follows from the first one by 3.16, again, just switching the Q and P positions around. Finally, 3.15 follows from 3.16 and 3.14. Just substitute the simpler side of 3.14 into the right side of 3.15, and what you have is 3.16, which is something we've already proved. Okay, so relatively easy to prove all of the logically equivalent versions of probabilistic independence. Okay, now we know what it is for 2 items to be independent of each other. We have basically 5 different equations to describe pairwise independence. Suppose you have more than 2 things, 3 or more. So let's just talk about a case where we have 3. That's what problem 3.9 is about. So what does it take for the entire set of X, Y, and Z to all be independent of each other? And one might hope that all you need is pairwise independence, but it turns out that's not enough. So we're supposed to come up with a case to show that it's not enough. So the claim would be if X is independent of Y, X is independent of Z, and Y is independent of Z, then X is independent of Y and Z. But it's easy to provide a case where that's not true. So assume the first 3, and you want a case where the 4th one is false. So here's my example. Let A and B interact in such a way to produce a poison that kills, even though neither alone does anything at all health-wise, and where there's no connection between taking the first and taking the second. Like if you take the first one, it doesn't incline you to take the second. If you take the second, it doesn't incline you to take the first. They're just completely independent of each other. Then let X be the claim that S continues to live, Y be the claim that S ingests A, Z be the claim that S ingests B. Since either alone has no effect on health, the first 2 equations are satisfied. Continuing to live is independent of consuming A by itself. Continuing to live is independent of consuming B by itself. And consuming A is independent of consuming B. We stipulated that up front. Yet the probability of continuing to live is near 0. Maybe it is 0, given the taking of both A and B, so it's much lower than the probability of X itself. Okay, so pairwise independence isn't sufficient for complete independence across groups of 3 or more. Now, 3.10 we are going to skip because I don't want to require you to have Mathematica for purposes of this course. There's first the cost of the program. I don't know if you'd have to buy it. I don't know how that works. But the other thing is I don't want you to have to spend time learning how to use a program. Maybe most of you already know how to use it. It's a fancy program and very, very nice. And PRSAT works within Mathematica. It was written by Brandon Feidelson. who is Mike Titelbaum's dissertation director. And what it does is it generates a model, a credence distribution model for any particular inputs that you want to give it, if a model is possible. Of course, sometimes the credence stuff that you input will be incapable of having a probabilistic model, but PRSAT finds a probabilistic model if there is one. So it's a pretty neat program. I've played around with it a little bit, but I don't want to require it. So we're going to skip this problem. Let's move on to Reichenbach and 3.11. Okay, so you've got 4 conditions, and these describe a causal fork. So in the presence of C, the link between the probabilistic relevance of A to B disappears, so that you can just multiply to get the probability of the conjunction under the supposition that C is true. But the credence for A given C is greater than for not C, and the same for B. So that constitutes a causal fork, and we're supposed to say some stuff about it. In particular, assuming that C is the common cause of A and B, explain what each of the 4 conditions means. Well, 1 and 2 tells us that C is positively relevant to A as well as B, which is what you'd expect from a common cause of both of them. While 3 and 4 tell us that the conjunction of the 2 is probabilistically independent of each of the conjuncts when we assume either C or its denial. All right, now here's a tough proof, and I don't want to spend a lot of time on this. This is a very hard proof. It was proved in Hans Reichenbach's book in 1952. Here's what he says. I'm going to assign just a bunch of, he says he is going to assign just a bunch of variable letters for each of the probabilities. So probability of A is going to be A, probability of B is going to just be little b, C going to be little c. Then he uses W for the conjunction of A and B. He uses U for A given C. He uses V for B given C, R for A given not C, and S for B given not C. Now, notice that's all of the probabilities relevant to the 4 conditions in the causal fork that we're talking about. Now, I'll let you verify this for yourself, but using this rule of expansion, we get 3 formulas. One telling us what the probability of A and B, which is W, what that resolves into. So it's the probability of C times the probability of A given C times the probability of B given C plus 1 minus the probability of C times probability of A given not C times probability of B given not C. So that gives us an equation which tells us what the value of W is. We get a similar equation for the probability of A and another one for the probability of B. Now notice what we're being asked to do is find out the relationship between W, A, and B. And what we're supposed to show is that W is strictly larger than the product of A times B. So you can then factor these equations. He calls them simple computations. You get from these equations that W minus A times B equals C times 1 minus C times U minus R times V minus S. Notice U minus R and V minus S are the inequalities in the first 2 conditions above. Now we have to assume that all of the probabilities here are defined. So we're assuming that C is strictly between 0 and 1. Because of the relations conditions, 3 and 4, the expression on the right is greater than 0. Therefore, W minus AB is greater than 0, from which it follows that W is strictly larger than A and B. Okay, so the crucial things to figure out if you want to see your way through the whole thing. It just takes, this problem takes inordinately long to see your way through. But given this rule of elimination, you can generate each of these formulas for what W, A, and B have as their values. And then you have to be able to do some simple algebraic factoring to get to this formula. And once you do that, then you can see that W minus AB is going to be a positive number. Okay, so enough of that one. That really was a hard problem. I mean, it was one of those novel results in Reichenbach's work in the 1950s. And I mean, he's the first person to work on screening off and causal forks and stuff like that. So not many people pay attention to his work anymore. It's actually been supplemented, or supplanted, I guess is the right word, by work on what are now called Bayes nets. And the generalization of causal forks are called Markov chains. So if you're interested in either of those, that's something that goes beyond what's in the textbook. But it's for that reason that Reichenbach's causal fork stuff is not discussed that much anymore. But in the 1950s, this was a novel discovery and an important one. And so being able to come up with a proof like this is probably more than should reasonably be expected in a course of this sort. And this isn't the only homework problem that is probably so advanced that it's unreasonable to expect anybody to get it. I guess what we could have done is put stuff like this on the exam for extra credit. But given that the proof exists in the literature, it's not really a fair question to do for extra credit, because then you all know how to do Google searches and you could find this proof and then you could put it on your exam, which would get you points and you'd be happy. But it's not, it strikes me as not a fair problem in the homework, and wouldn't be a fair extra credit problem either. So 3.12 is going to be on the take-home final. It has 3 parts. So let's move on to 3.13 and talk about it. Okay, here's a fact according to Mike. For any propositions P and Q, if the credence of Q is positive, then the credence of the conditional is greater than or equal to the conditional credence. Okay, so we start from a language with atomic propositions P and Q, and we're going to build a probability table on its state descriptions and use that to prove the fact above. So what we're supposed to be showing is that as long as Q has a non-zero probability, credence for the conditional would be greater than or equal to the conditional credence. Okay, so here's a table. Now this table can't prove the general fact. No table could do that. It can illustrate the general fact, but it can't prove it. You'd have to prove it. You got to do more than just construct a table and plop down some credences. In any case, I built a table, plopped in some credences to illustrate the fact in question. And what's crucial is that the sum of lines 1 and 3 has to be non-zero. And it is. So what's the conditional credence? Well, P given Q is P and Q over Q, so that's 0.1 over 0.5, which is 0.2, and the probability for Q horseshoe P is the sum of the not Q lines or the P lines, and that's 0.6. So it illustrates the fact in question. This probability is greater than or equal to the probability of P given Q. So that's what we were supposed to prove. Now, this is a longer and harder proof. So equation 3.49 is sometimes called the equation. The equation identifies conditional probabilities with the probability of a conditional. So we're going to assume that equation is true, and then we're supposed to show that this requires that either the credence of Q is 1 or the credence of Q horseshoe P is 1. One of those two things is going to have to be true. Now, this is just a simple algebra problem. So I've included all of the steps to solving the problem, but let's make sure we get the setup correct first. So we start out with 3.49, and referring to the table above, the probability of the conditional is the sum of the credences for lines 1, 2, and 4. The conditional probability is line 1 divided by the sums of line 1 and 3, lines 1 and 3. That's the ratio formula. So 3.49 becomes the value for line 1 over the value for 1 plus the value for 3, and that equals the value for 1 plus 2 plus 4. Now we know that the sum of all the lines is 1, so we know that V1 plus V2 plus V4 is the same thing as 1 minus V3. So with all that, here's the formula we're trying to solve for. V1 over V1 plus V3 equals 1 minus V3. So turn this into a simple problem to solve for x, where we let V1 be x and we let V3 be y. So we have x over x plus y equals 1 minus y. And now solve for y. Solve for x. And here's what you get. The answer you get is that x is minus y plus 1. And since probabilities have to be between 0 and 1 inclusive, this solution can only solve our problem when x is 1 or y is 0, or vice versa. If y is 0, then the probability of the conditional is 1, since that is the value for the state description at line 1, which is one of the lines that generates the probability of the conditional. So suppose y is 1. That's the value of line 3, one of the lines that generates the probability of Q. So the probability of Q would then have to be 1. So either way, one of the two probabilities has to be 1. So as always, if you want to follow up about anything in the homework or in the chapter that doesn't show up in the homework, send me an email. We can either communicate by email or we can set up a Zoom phone conversation, video conversation, I guess. Just let me know. In any case, enough on chapter 3. We'll turn to chapter 4 in the next one.